Well, welcome back to our course on system engineering. We have now completed the first major section in this text in the course that's with our flow of lectures. It's Falling with Booty, the main textbook. And so now that we've done this introduction, overview, and basic knowledge, now we're going to get into the very detailed specifics about the design and integration process. And so there's going to be a logical flow of going through the life cycle of how we do system engineering development. And so this first lecture is going to be on requirements and defining the design problem. So in terms of an overview, this chapter will explore requirements development approach as a systematic process. And the systematic process involves the definition of an operational concept of the system, including usage scenarios, a description of the involvement of the system with other systems, and an objectives hierarchy of the stakeholders across all phases of the system's lifecycle. A partition of requirements is employed to discuss the systematic approach for defining requirements. You might remember in the last couple of lectures, we talked about discrete mathematics and graph theory. And so you're going to see some of those influences in the way that this material is gone through. For example, when we talk about partitioning. And so maybe you might want to be thinking about what we covered in the last couple of lectures at a high level, trying to not get too buried into the weeds of those topics. And hopefully we can begin to see how that might actually have applicability in real life system engineering problems. Okay, as I am going to do, I'm going to refer to some of our supplementary textbooks for additional information. And so this is from a practical guide to SysML. And so this is a generic example of a requirements document. And so as you see within SysML, we can have this type of view, something called a REQ. And so we have like a top level requirement, and then we can have a tree that you can have layers of requirements that are below this. And so you can have like an overall override operating environment. Below that, you can have an area where you talk about all weather operations, 24/7 operations, and then there's things that are related as you move your way down through that tree structure. So you have the rec ID, a unique number for a requirement. Then you have the text, and then you can have these additional fields that can be useful for, say, here we're showing derived, verified by, refined by, and so these other types of descriptors that can be some additional information that will be included. So that's just a reference for you to be thinking about. An interesting question is to define what exactly is a requirement. And I'm not going to read these in detail, but here's a couple things from the MIL standard 499B, accomplishments levels needed to achieve specific objectives, attributes of the final design, user need or necessary feature, function, or attribute of a system. Those are examples of what you could think of as a requirement. An essential attribute for a system or an element of a system, or a mandate that something must be accomplished. And so those are all examples of what you could be considering a requirement. So here is a context for requirements. And so you can have the overall mission. What exactly are you trying to accomplish? And so you can think of whatever system you might like. So if you think of GPS, the global positioning system, the whole goal of the mission is to provide position, navigation, and timing to the users. The stakeholders' requirements are then going to be more details that are supporting that, and then is then the basis for which an entity, a company, will start to flesh out a design. So they're going to be responding with their system requirements that codify everything they get from their stakeholders, and then put it in the types of terms that's necessary for them to create a design. These are examples of derived requirements. So you have the system requirements. Below that, you have the component, And then you have the configuration items that would be elements below the component. So that's a general flow of how that works. There's going to be 3 slides in this lecture that will come back to this pragmatic principles. And so this is the first pragmatic principle, number 1. And this is know the problem, the customer and the consumer. We'll come back to this idea in terms of effectiveness criteria to help make system decisions, and then enable and management requirements. But here, there is a lot of details, and I'm just going to quickly give an overview of this. And you can read through this in more detail as well as look at it in the textbook. And so become the quote customer/consumer advocate and surrogate. So for a system engineer, you're going to be showing that you're going to be working closely with the customer and helping to make sure that they have a clear idea of what the solution is. A lot of times they have an idea, but they don't necessarily have it formulated into a concept that you can actually build. From there, you want to begin and validate the customer's needs. And so you want to help them clearly define what the problem is. And so have an idea, what is the domain that they're trying to focus on, have a problem, come up with a problem in a solution independent terms. And so you want to have that not be based on a solution. The solution is something that you want to trade based on a number of different things. You want to know the customer's mission and objectives. That's going to be important. You do not want to assume that the original statement of the problem is necessarily the best. So there can be some evolution and some give and take that would happen over time. And so the system engineering folks would be critical in helping that out. When confronted with the customer's needs, you want to consider what smaller objectives are key to be satisfying that need. And so how do you start to break that down into, say, key performance parameters? You want to determine the customer's priorities and then stick with the ones that are most important, but there could be performance, cost, schedule, risk, or some combination of those. You want to probe the customer for new product ideas and problem shortfalls, and maybe they haven't clearly specified so far. And so there is an ongoing conversation. You want to work with the customer to identify the consumer groups. You want to use a systematic method for identifying the needs and solution. You don't want to depend on written specification and statements of work. The face-to-face sessions are important, and then you codify that in the things that you write down or put into a model-based system engineering tool. You want to state as much of each need as quantified terms as possible. You want to specify as much as needed to make sure that you capture what is wanted. And finally, you want to clarify each need by identifying the power and limitations of the current and projected technology. You have to use some level of technology, and so that's the thing that you eventually need to be focusing on. So that's our first of those 3 pragmatic summaries that we'll be going over. So let's talk about some definitions. And so we're going to talk about systems, system task, human design system. So a system is a set of components acting together to achieve a set of common objectives. And so a system task or function is a set of functions that must be performed to achieve a specific objective. And so there's going to be a variety of functions that are going to be part of a system. A human design system has a variety of different components. So there's a specifically defined set of segments that's going to have a set of interfaces, and it's going to be designed to achieve a common mission or function of a fundamental objective. It's going to be subject to a set of constraints. And finally, through the accomplishment of a predetermined set of functions. So just some context, and we have used this diagram before, but we want to be thinking in terms of the context, both internal with the direct external systems, and also it's a larger context that it has to be flowing in. So the external systems, as we're showing in this figure, that we're thinking about the external systems can impact the system and the system does not impact the external system. So there can be this input and output of possible things that can be going on. The context of a system is a set of entities that can impact the system but cannot be impacted by the system. So we're seeing this a couple of different times in terms of a perspective that we would like to keep in mind. Okay, I'm going to have a couple of different ways of showing some of these slides as we work through these chapters. One is directly going to a SysML, and so a block definition diagram. And then I'll not go in as much detail, but go over the IDF0 version of this. And so in this block diagram, we're showing how things take a progression of starting with you wanted to develop the operational concept. And then there's several things that need to take place as a result of that, that there's going to be an iterative process between developing the boundaries within the external system. There's going to be the process of develop, analyze, and refine the requirements and develop the system objective hierarchy. And so there's a couple other activities that we need to be doing in requirement feasibility. We need to define the qualification system requirements. And so that's going to be going back and forth in the develop, analyze, and refine the requirements. And then the outputs of these things are going to be used to finally obtain approval of the requirements document. So from a SysML point of view at a top level, that is a way of capturing that development. In an IDF0 point of view, we're capturing the same thing, and as a result, I'm not going to go through this in much more detail, but there's more connections that are highlighted here. And so you can see that there are some pros and cons for using each one of these. So for an operational requirement document, and that's typically what ORD stands for. We're talking about originating requirements development. So before in discussing the requirements, noted that the requirements must be developed for each phase of the system. So the life cycle phases used in this course, as well as the textbook, are here: the development, manufacturing, deployment, training, operations, refinement, and retirement. There's a strong correlation between the stakeholders and the life cycle phases, that they're going to be involved in the development. The company or system integrator is going to be the primary go-to person for the development and manufacturing, but the customer is going to be involved in the approval of that. And then you get into the operations, refinement, and retirement, and the customer is going to have a say when those things will happen and what would be the things that you might be doing for refinement, and ultimately how and when you're going to do the retirement. So there's a couple charts here are talking about roles and responsibility and requirements generation. And so who has a right to have an operational requirement? And so the answer would be any individual organization with an operational need. What does one call require? You can be thinking that as a customer or stakeholder, and you've been hearing me use those terms. Who must respond? And so the systems requirements team, so the company, contractor, or contracting team is the ones that are going to be responding to the requirements or the proposed requirements. And by what criteria does the system requirements team respond? They establish the external system diagram and fundamental objective hierarchy of the system. So continuing on, how does one know that a requirement is, quote, right? And there is no right or wrong answer, but only what is acceptable or unacceptable. And so that's the dialogue that goes on between the stakeholders and the developer. How are these requirements conveyed? The requirements, the systems requirement team documented the collected requirements into the originating requirement document or operational requirements document. There's a couple possible ways you can be thinking of that acronym. And what does the system requirement team do next? The requirements team remains active throughout the whole system's life cycle, and maybe that there would be some changes or other things that need to be finessed as it goes through that development process. In terms of categories, there's a variety of categories for specifications and thinking about their level. You can have the originating, the derived, the implied, and the emergent. And so all of these things are what has to be captured as you're developing or refining your design. So we can be thinking of performance requirements versus constraints. Think of the applications, the system versus program, and then think about the functional interface or system-wide in terms of categorization and functional decomposition. Okay, we had talked about sets, partitions, and things like that, functions, and when we just talked about discrete mathematics. And so here we're seeing some of that terminology come up. And so we have these categories or partitions of requirements, input and output, technology, and system-wide trade-off. And so each of these things can be starting to be looked at, and we can be creating an objectives hierarchy. We can doing a trade space for how we're going to be doing different things. And so trade with cost, performance, and cost performance both together. And so those are the things that we're going to be in the mix for doing a requirements development. So for exemplary requirement dimensions, we have the input or output performance. And so there's various things that we can be thinking of that: the quality of the output, the quantity of the output, the timing of the outputs. We can be thinking of the undesired or unexpected inputs, unexpected or undesired inputs and appropriate responses. These are bounds on expected inputs and appropriate responses. And finally, the interface constraint to this, the required format of an input or output as defined by the interface, timing constraints, the physical form or fit of an interface. And then continuing on, suitability or quality issues of the system. And there's a variety of different things that we're listing here. Sometimes I've heard the term the illities. You can see like availability, survivability, supportability, trainability, testability, extensibility. So all of these quality measures that we want to be considering. For cost for various life cycle phases, we can be thinking about the affordability of the system, production cost, development, the deployment, training, and decommissioning costs. We can think about schedule for various life cycle phases, and so the development, manufacturing, training, deployment, and durability. So those are some additional things that can be what we would have to be considering. Then we have something that Booty calls the stakeholders requirement document. Maybe you could shorten that to SRD, but that has some other implications or use by different type of entities. But here's just an example of the types of things that could be included. An overview, the applicable documents, and so these are a rough general flow of how a document would go. The section 3 would be the details of the requirements, and then we can have, maybe you're going to be doing it by phase, and so that's how we're showing it here. And then the appendices that you might need for additional information that may not be so focused on the details of requirements, but useful information to help give some orientation. So here are examples of the characteristics of sound requirements, and writing good requirements is necessary, and having the right type of rigor to make sure that you clearly are articulating what needs to be done, that is important. So you can be thinking of individual requirement attributes, that they're unambiguous, understandable, correct, concise, traceable, they're design independent and verifiable. So here you're just looking at a single individual requirement that you want it to be clear, there's no overlapping requirements, that it's as short as possible, but making sure that it's correct and understandable to all the parties that are going to have to be playing it out. Then we have maybe thinking of a set of requirements that to define a function or a capability, you need to have a set of requirements that together that are acting towards a larger entity. Sometimes you might find requirements in a table. And so we're going to, once again, you want to make sure that the requirements are unique, that they're complete, that they're consistent, that they're comparable, they're modifiable and attainable. And so it can be a little bit tricky when you now have to have all of these things in concert for you to have a complete picture of what you're trying to do with the design. So let's talk about the more details, how-to of writing good requirements. First, for terminology, you need to have a shall. This is it's a contractual binding word that you want to be using. So that's really what you should be focusing on in your use. Will and should are really not some things that you want to be having in a good requirement. Requirements statement shall include a subject, the word shall, a requirement statement at the minimal acceptance threshold. So subject, a verb, and then a quantity. You want to avoid compound predicates. You want to have every requirement in a single sentence with a single requirement identification, and you want to be avoid ambiguous terms. So here's an example. The development system shall receive inputs from stakeholders. The manufacturing team shall have a scrappable rate of something. The deployment system shall accept. Training system shall complete. Training, the operational system shall have an operational life of X years, a certain number of years. The refinement system shall accept new technology for the central processing unit. The retirement system shall cost less than a certain dollar amount. So just some examples for you to be thinking. Use proper grammar, avoid compounds. You want to be avoiding negative predicates. So the system shall not, that's really something that you should avoid. You want to tell what the system shall do. And once again, avoid ambiguous terms, optimize, maximize, minimize. In terms of how would you verify that? Those are not very clear, including things like adaptable, flexible, rapid, robust, etc. And there's some more terms that you're seeing are examples. So how do you go about talking to stakeholders? A great way of doing this is through usage scenarios or use cases. And so this is one of the reasons in SysML that they wanted to maintain those types of drawings that are trying to articulate between the stakeholders and the developer what exactly is supposed to be done. You want to ask to observe their stressful periods. So you want to make sure that you capture not only just the best case examples of how things are going to operate, but in the worst case situations as well. Give them drafts to modify. So you want to make sure it's an iterative process. You want to be giving them choices. You can think of how an eye doctor, is it this or is it that? Maybe that's a mental picture for you to be holding on to, and work with them in groups. They can play off one another's ideas, and so that can help to come up with a better perspective on what the requirements should be. So you want to stop seeking requirements as late as possible. So keep that engagement going as much as is practical. And requirements related difficulties were responsible for 34 to 44% of project failures. So getting the requirements right early is going to help reduce the possibility of project failures. And so that's something to avoid. So we need to have at the very beginning as an operational concept of what exactly that you want to be doing. And so you can probably remember, or maybe you've seen videos of Kennedy stating he put out this put a man on the moon and bring him back safely by the end of the decade. And so he was telling exactly what was going to be done, and he also gave a schedule. So that's an example of having a vision and where you're going to start with. And from that vision, you're going to start to be thinking about the specifics of what that might mean. And so this is still capturing a lot of what would be at the vision phase, but you can see how this is starting to lend itself towards the mission requirements of how you're going to go about doing a injection to a lunar orbit, landing on the moon, launching from the moon, and then injecting back to Earth and then landing on the Earth. So that's just some more details. So then we can be creating an operational concept, an ops con, or you can be thinking of as a con ops. And so this is going back to the elevator for an example. And so we have a relationship between the passengers and the elevator. And so this can start to be played out with these types of details in an activity diagram or a sequence diagram. And so we're starting to show how that would work. For operating scenarios for systems, there are a variety of things that would be the initialization of the system, the steady state operation, the extremes of operation, standard maintenance mode, resupply modes, failure modes due to an internal issue, shutdown and termination. So here are just an example of the scenarios that you would be mindful as you're trying to do a complete system design. So for the external system diagram, we're coming back to this diagram we've seen in a couple places. We wanted to define the boundary of the system. So think of a composite of the scenarios with the operational concept. And so we want to be showing the external systems and the context of the system that all this has to be based around as we're going forward with this design. Okay, I'm not going to go through the IDEF 0 diagrams again, but here is just an example for the external system diagram for an elevator. There are special rules that you can be thinking about for an external system diagram. All of the outputs of the system's functions, and each of the external systems must receive at least one input. So the outputs of the system's functions have to go to at least one of the external systems, and the external systems must receive one output. And so there has to be an input and an output between these interfaces. So in terms of objective hierarchy, you can be thinking of objectives of what are the key performance parameters, and there's usually only a handful of these that are key for the overall mission. And so there is a minimal acceptable threshold, and there can also be a desired stretch goal for the performance level that can be codified in the requirements. And then there's a hierarchy that integrates all the objectives, and you're going to see the key performance parameters along with others. And so here are, for the elevator example, just to show you how it could look for an objective hierarchy. And so you have the operational objectives, you have operational cost and performance objectives, and then the performance objectives, there's a lot more detail, and even detail below those things that we're trying to show there. Okay, we're coming back to this pragmatic principles. And so this is the second one. The first one was know the problem, the customer and the consumer. And so you get close with the customer. You try and consider what is the perspective of the consumer and make sure that you have a good understanding of the problem. Now we want to be talking about the use of effectiveness criteria based on needs to make system decisions. So you want to select the criteria that have demonstratable links to customer consumer needs. This would be composed of operational criteria, program criteria, and internal integrated logistics support criteria. So these that you need to have your criteria laid out and agreed upon. So then it's basically just turning the crank, and you could be coming up with the effectiveness results. And so you're not just arbitrarily making a decision, but you have factual information based on analysis that has been agreed to when you go forward on that. You want to maintain a needs-based balance among the often conflicting criteria. So there will be conflicting criteria, and those are things you're going to have to navigate through. You want to select criteria that are measurable. And so this gets back to this effectiveness. You need to have metrics. And then from those metrics, you're going to be able to continue to assess performance. You want to use trade-offs to show the customer the performance, cost, schedule, and risk impacts of the requirements and the solution variations. So if we go with option A versus option B, here's the pros and cons. Let's make this decision, and we will try and inform you as best we can. But ultimately, the customer has the final say. When possible, use simulation and experimental design to perform trade-off. And so model-based system engineering, which is one of the things we're trying to highlight in this course, is one of those key things that we're going to be doing as much as possible. Have the customer make all value judgments and trade-offs, and finally allow the customer to modify requirements and participate in developing the solution based on the trade-offs. So this is something where we can be starting to think about the objective hierarchies, and we can have the various models, and then there's values and thresholds that we can start to define for each one of these. And so we can have, this is shown for an elevator system, so we can have cost and the operational effectiveness. We were showing a chart earlier with some of the key values that we might be thinking about here. Here is the objective hierarchy. Now where we're showing it, well, let's play this out with some modeling or some testing, and you can actually get these curves, and you can figure out where exactly on each one of these things are you willing to live with, and have an aggregate of a effectiveness and performance, and come up with a satisfiable way of harmonizing what would be acceptable. Prototyping is another great way of starting to reduce risk and to strengthen your awareness and understanding of the design. So you can have a physical model of the system that maybe it ignores certain aspects of the system. And so you model what is necessary to answer the questions that you're trying to address. You can have a throwaway prototype, and so this is educating the users on the possibility, maybe stressing it beyond normal values, so you can see how it would degrade and various things. And then you can have evolutionary prototypes where you start to look at, well, what if we turn the knobs a little bit here because we're trying to squeak out a little bit more performance. And so those are another example of what you can do with prototyping. You can have usability testing, and so you can obtain samples of the users and see how they actually engage with the system. You can elicit reactions, try and find out what they think of as a result of them engaging with the prototype. And then there's these things like learnability. How long does it take them to master the way the design is set up? The efficiency, what is the time for a frequent user to complete a defined task? Does there need to be more ergonomics for this to make it more usable? Memorability, how easy is it for a user to do a task and then remember how to do it the next time? Maybe they don't do it on a daily basis. What is the error statistics for the human in the loop making a mistake? And finally, what is the satisfaction? What is the stress level associated with the use? And is there a fun level associated with the use? If people like using something, they're going to continue to use it. So that's just going to be an important thing that you want to be observing. So for defining the input and output requirements, the external system diagram is a primary tool. And so you're trying to establish those boundaries and then establish how you're going to do those interfaces between what's within the system and what's outside it, both the things coming into the system and the things going out. The system engineering team must examine each input, control, and output in detail to discover every requirement associated with each of these items. The system context should be addressed in the requirements. The interface constraints address the physical aspects of the interface to which the system has to connect to obtain the inputs and disseminate the outputs. And the functional requirements should be 2 to 6 functions that partition the system function. And so here we get back to this idea of partition. Partition means that there's no overlap. So there has to be each unique thing that they don't share any features. And so each function that is part of a system has to be unique. And so here we're using, say, on the order of 2 to 6 functions in the partitioning of a system. So you can be thinking of exemplary input outputs. Elevator shall receive calls. Elevator shall indicate to a prospective passenger that they have called the elevator. The elevator shall use a standard phone line from the building for emergency calls. And so those would be examples of inputs and outputs for the elevator example. For system-wide and technology requirements, and so you're going to have a technology baseline that you're going to have to live with. One of the technology requirements are the ones that engineers would prefer not to have, because they really do constrain the engineering creativity. And so you want to be aware, and so you don't want to be putting requirements in technology, but try and focus requirements on capability. The cost requirement deals with payment of money, and a schedule requirement deals with the timing issues for the relevant system. For trade-off requirements, you want to incorporate the value judgments within and across the stakeholders. You want to sample many stakeholders, and bill payers ultimately are responsible for integration across the stakeholders. And this is something that we'll be talking about in more detail. So for qualification requirements, you have observance, verification plan, validation plan, and acceptance plans. So you have these different types of plans that you're going to be using to help you go through the whole qualification process. And we'll be coming back to that later, so I'll just continue on and not spend too much time on that. Here's just a diagram showing the stakeholders requirements development process. And so you start with an operational concept. You need to be thinking about, well, what is the externals? So you have to bound what your system is. You need to have a hierarchy of requirements. And so these all fold together into what are the requirements that started out with an operational concept. And then with prototype and analysis and elicitations, you can help to give some clarity and help the stakeholders have higher confidence in the design that they are starting to define in terms of the requirements. For requirements management, you want to have a way to have the identification, derivation, allocation, and control of the requirements. You want it to be in a consistent, traceable, correlatable, verifiable manner, and all the system function attributes, interfaces, and verification methods. And that you want to make sure that it all includes the things that the system must meet. Okay, this is the last chart, and here we're coming back to this pragmatic principle 3. And so the first two, we talked about know the problem, the customer and the consumer. Next, we wanted to have the effectiveness criteria for making decisions, and so you need to have metrics. And finally, you want to be thinking about the established and managed requirements, and we've talked about this already. So you want to identify and distinguish between specified, allocated, implied, and derived requirements. So you need to be you need to distinguish between the categories of requirements. You want to carry analysis and synthesis to at least one level broader and deeper than seems necessary. Therefore, your analysis is complete. You want to write rationale for each requirements, ensure that the customer and consumer understand and accept all the requirements. You want to explicitly identify and control all the external interfaces. You want to negotiate interfaces with affected engineering staff. You want to be sure that you document all the requirement interpretations in writing. And so you just don't have something that may not be as clear as what might be necessary. So you have that supporting agreements in place. You want to plan for the inevitable need to correct and change requirements. You want to be careful of new fundamental requirements that could really break the bank in terms of avoiding something that you could really damage your ability to perform. And so this is sometimes called requirements creep. And finally, you wanted to maintain the requirements traceability. Okay, well, that's it for this chapter and this lecture. So thank you very much.